Hello and welcome. My name is Johan, and I'm very pleased to have the opportunity to present about my research with the title of Enhancement of Steam Condensation through Surface Wettability Modification. Let's begin. So as we all know, the world's energy demand keeps increasing, and the most common type of energy generation is by utilizing steam power plants. Therefore, to economically and sustainably cope the increasing energy demand, the steam power plant's efficiency must be increased, either by increasing the boiler temperature or the hot side, or lowering the cold side, the condenser temperature. But due to limitations of material, lowering cold side temperature is more feasible. In other words, to increase power plant's efficiency, we should increase the condenser effectiveness. So in a steam power plant, the turbine exhaust steam enters the condenser to reject heat, and with a more effective condenser, the TTD will become smaller. And the TTD is defined as the temperature difference between turbine exit steam and condenser exit cooling water. And it is also associated by the decrease of condenser pressure, which leads to a higher work output. As we can see on the figure on the right, as TTD drops as much as 8 degrees Celsius, the overall steam power plant efficiency increases by 1%, generates savings potential as much as $33 billion per year, and the CO2 emission drops by 2.3%, potentially reducing 245.2 million metric ton CO2 per year. As we can see, the video shows the wettability of superhydrophobic and superhydrophilic surface, and the wettability indicates how easily a liquid sticks to a solid surface. To have superhydrophobic characteristic, we would like to have a low wettability. It is done by lowering the surface free energy, since surface energy refers to the energy needed to create a new contact surface area. In this case, it is done by applying a silicon polymer called PDMS, or polydimethyl siloxane. So when a liquid is dropped on the superhydrophobic surface, the droplet will bounce and it will not stick to the surface. By having a superhydrophobic characteristic, the heat transfer from the steam to the outer tube surface is free from resistance, since there is no condensate hindering the heat transfer. Unlike hydrophilic, the film of condensate acts as a thermal insulation for the heat transfer to the tube surface. As we can see, the heat transfer coefficient for dropwise condensation is significantly larger than that of filmwise. Meanwhile, superhydrophilic surface promotes filmwise condensation. However, as vapor keeps condensing, the contact angle of the condensate becomes larger as time goes on, similar to dropwise condensate. Furthermore, filmwise condensation is more effective than dropwise condensation in terms of water harvesting capability. This outcome challenges the common belief regarding the heat transfer performance of dropwise is better than that of filmwise condensation. And here is the setup of experiment. The water supply for the steam generator and cold fluid is city water, since it has a constant temperature. So city water fills a 45-liter container with submersible pump placed inside, pumping the water through the condenser tube connected by hose. And this pump was set to be in its maximum capacity. And from the condenser, the water is discharged to be disposed. Note that the thermocouples are installed through the hose directly adjacent to the protruding tube, inlet and outlet. And as for the mass flow rate of the cooling water, it is measured directly using a digital scale, and the outlet is discharged to container for 10 seconds, and it was done 10 times. And regarding the supply of steam, the steam generator has a capacity of 40 liters of water and can reach a maximum temperature of 120 degrees Celsius. It has a water level control, which requires the tank to be full enough to activate the heating element. And throughout the experiment, steadiness is maintained by fully opening the output valve while heating the tank. The output valve of the generator is connected to the condenser using hose with thermocouples installed. The steam temperature just before entering the condenser remains consistent, ranging from 97.4 to 97.7 degrees Celsius. The steam generator was placed on an industrial weighing scale, while its readings monitored by the camera to record data. And since it operates no longer than an hour, data is recorded every 5 minutes for 55 minutes. Furthermore, it is proved to be in a steady state since the mass for it is constant. The condensate from the condenser is discharged to the outlet port with thermocouples installed to measure the temperature. Then, the condensate is collected with a container and its weight is measured. And this is the actual setup. And there are some modifications to support the experiment. And one of them is there are 2 additional thermocouples attached on both ends of the heat exchanger. And this is done to monitor the steadiness of the system, since the condenser wall temperature increases when steam enters the system. Eventually, the wall temperature remains constant at about 80 degrees Celsius. And the heat loss to the surroundings with a temperature of 20 degrees Celsius is no more than 70 watts. So it is small enough to be neglected, since the heat transfer to the cooling water is about 1800 watts. The construction process is preceded by determining the required tube length to condense all supplied steam fully. However, the mass flow rate of cooling water and steam was unknown at the time. Furthermore, the outlet conditions were unknown too. Therefore, epsilon NTU calculations method is used for this purpose. And some assumptions required for the calculations are made, such as the mass flow rate of cooling water and steam. And the design calculations yielded a line of 633 millimeters length. The tube material should be conductive to suppress the thermal resistance. Therefore, the copper tube is chosen. And furthermore, the tube of the heat exchanger should be possible to be replaced frequently at ease, because there are several tubes needed to be evaluated. Also, the coating process for fabrication of coated tubes should be done easily. So therefore, 2 straight tubes with almost half the required tube length is welded to a 2 centimeter wide U-bend connector. And here are the experiment data collected. So the graph shows the steadiness of the system. The provided temperature data is used to calculate the heat transfer to the cooling water, and it will be used to calculate the condensation coefficient. However, there was no significant temperature difference between bare copper, superhydrophobic, and superhydrophilic tube. As we can see, the condensate temperature represented by the purple line is unstable due to inconsistent flow of condensate coming out or dripping through the outlet port. But when the liquid makes contact, a proper contact with the thermocouple junction, the temperature readings rise. Therefore, the maximum recorded value is the best representation of the actual temperature of the condensate. The table below shows the substantial sensible heat transfer only occurs in the cooling water, although there is a slight sensible heat transfer from the condensate, but it is negligible. So the evaluation of heat transfer coefficient are conducted empirically and experimentally. For the empirical evaluation of film wise relies on the classical Newsett model, which considers the saturation temperature of the steam and the surface temperature for condensation. The surface temperature is calculated from the water temperature and the thermal resistances, as direct measurement is not feasible. In contrast, for droplet condensation, the literature value of heat transfer coefficient on treated copper is used as a benchmark. Meanwhile, the experimental evaluation is based on the epsilon NTU method to calculate total thermal resistance and subtract it with other thermal resistance to obtain the coefficient due to condensation. The initial length of 63 centimeter has a large amount of error, as we can see, to the relative to the empirical value, with the arbitrary limit of error is 30%. This is due to the cooling capacity of the heat exchanger is larger than the heat removal to condense all the supplied steam. Since the mass flow rate of steam is fixed, the length must be shortened. And after calculations, the updated length is 243 millimeters. And for the 67 millimeter tubes, it's just a test. It is just a test to see whether the experimental value is getting closer to the empirical or not. The evaluation of various tube length shows that the 243 millimeters tube generates the least amount of error relative to the empirical value. Therefore, the comparison of treated and bare tubes are performed only for the 243 millimeters length. And as we can see, there is no significant improvement of coated tube relative to bare copper. And superhydrophilic surface induce a 20% decrease, meanwhile superhydrophobic generates only 4.5% improvement. So the unnoticeable difference of heat transfer coefficient was caused by the limiting factor of high convective thermal resistance due to the internal flow of water. Based on the figure at the top, there are three thermal resistances in series, which are due to condensation, RC, conduction through the tube wall, or W, and the internal convection through the internal flow of water, RHI. Heat transfer may be expressed in terms of logarithmic mean temperature difference and in terms of cooling water temperature difference. By rearrangement, the total thermal resistance is related to the outlet cooling water temperature. And note that other properties remain constant, and there is no temperature difference between inlet and outlet condensing hot fluid. If the thermal resistance of conduction and condensation are very small relative to the internal convection resistance, the outlet cooling water temperature increasement would not be noticeable and may become as error. Therefore, the measurement of heat transfer coefficient is not accurate enough. Furthermore, another possible cause of the unnoticeable coefficient difference is that the coatings were found damaged after the experiment. The superhydrophilic surface was found damaged after the experiment. As we can see, after about 1 hour of steam exposure, this tube has lost its superhydrophilic properties. Instead of forming continuous film, water droplets began to attach to the surface, indicating reduced wettability. Also, the coating's pitch black color faded, and it suggests degradation. The surface before and after experiment are analyzed under SEM. It shows that the coating has grooves all over, but the width of the grooves is parallel to the degradation of the coating. The damaged coating has a maximum width of 7.4 micrometers, while the untested has 1.7. So the damaged coating has a larger inactive area compared to the untested surface. This explains why the wettability properties has gone, and therefore there is no difference between the damaged superhydrophilic and bare copper surface. And for the superhydrophobic surface, the figure on the left shows that right after the experiment, it was covered by condensate in the form of droplets. Dropwise condensation happens while the experiment took place, but the right figure shows that the degradation of the surface of the original superhydrophobic coating is not able to attract water. However, when the surface is already dried out after the experiment, the wettability properties of the surface alters like the bare copper surface. Also, the pitch black color faded. So it is concluded that the superhydrophobic coating is damaged after the experiment. So it is concluded into 2 points. The heat transfer coefficient measurement is not accurate enough to show the enhancement of coated tube. This is due to domination of other thermal resistance. In this case, is the internal convective resistance. This causes the increasing value of heat transfer, but not be noticeable even if there is a substantial increase of condensation coefficient. Current coatings are too fragile to be thoroughly evaluated, since they only withstand under 1 hour of steam exposure. And there are 3 recommendations. Stronger coatings should be studied as an alternative. Another method with higher accuracy for measuring the heat transfer coefficient is needed. This may be done by lowering other thermal resistance so that the dominating thermal resistance is due to condensation only, or by directly measuring the surface temperature on which condensation occurs. And if similar setup will be used, we should reduce the shell outlet port diameter or increase the condensing rate so that the condensate temperature measurement is accurate. That is all from me. Thank you.